precipitate form, or will I not? If I mix two different solutions together, I can look to see whether or not a precipitate will form by knowing whether or not a substance is likely to form a precipitate, is it likely to become insoluble quickly, and by determining what the KSP is for said substance. If I look at the concentrations of the ions in a solution that I make, and the ion concentrations are in such a level that they are greater than the KSP for the product of those ions, well then we have more ions than the water can maintain in solution form, and the excess will precipitate out. If the amount of ions I have in a solution are less than what the KSP would be for the product of those ions in a solution, then I have less ions than the water is capable of supporting. The water can clearly keep contained in the hydration shells much more, and no precipitate will form. The following set of rules would allow us to solve problems involving mixing two different salts and determining whether a precipitate would form. We're going to work through a sample problem together, and in the sample problem we're about to work through, I have matched each step here in the list to where I solved it in the problem. The problem that we're going to solve today can be found in your textbook on page 619, and it's question 25A. This is about the hardest level of problem I'd ever ask you to do in terms of precipitate formation. The question's asking us what would happen if I mixed equal amounts of a solution of 0.1 molar lead nitrate with 0.03 molar sodium fluoride. Would I get a precipitate or not? Follow along on this page in your notes as we go through the explanation. I'm going to break this down step by step by step. So the first thing we're going to have to do is take a look at the two salts we're mixing. We're going to be mixing lead 2 nitrate with sodium fluoride. Now, this is going to be a double displacement reaction. I know lead forms a charge of +2, and that can combine with the fluorines with a charge of -1 to give you my PbF2, my lead 2 fluoride. I also know sodium with a charge of +1 is capable of combining with the nitrate ion, which also has a charge of -1, to form sodium nitrate. So this is the double displacement reaction that possibly could take place. Once I have a double displacement reaction figured out, I need to take a look at the products and the reactants and determine whether or not any of these would likely to be a precipitate. Lead nitrate will remain aqueous in solution. Our solubility rules say that anytime a nitrate ion is present in a compound, that compound will remain aqueous and will readily dissolve in water. By the same token, sodium nitrate would also stay dissolved in water, as it also contains the nitrate ion. Again, compounds containing nitrate ions are very soluble in solution. The sodium fluoride would also be soluble in solution. Solubility rule 1 says that compounds containing group 1 ions are very soluble in solution. So our likely precipitate would be the lead 2 fluoride. Our third solubility rule says that halogen-containing compounds are typically soluble in solution unless they're combined with silver, mercury, or lead. So clearly, lead 2 fluoride is something that could precipitate out in solution. In order for us to determine whether or not we have enough lead 2 fluoride to precipitate out, or whether there is so little in the water that the water can keep it dissolved, we're going to have to figure out how much lead ion is in our water, how much fluoride ion is in our solution, and then compare it to that maximum amount that we can get from the KSP. Let's start by adding the lead nitrate into a container. The question said to add equal amounts, and so the simplest number we could use here will be 1 liter. We're going to add 1 liter of 0.1 molar lead nitrate into our beaker. From our stoichiometry rules in grade 11, we know that if I take the molarity, 0.1 molar, which is the same as saying 0.1 moles are found in every 1 liter, and I multiply that by 1 liter, then in this container, when I poured in a liter of solution, what I have essentially done is added 0.1 moles of lead nitrate into the solution. Since lead nitrate separates to form 1 lead and 2 nitrates, this solution now contains 0.1 moles of the lead ion and twice as many, or 0.2 moles, of the nitrate ion. We're now going to add to this a liter of 0.03 molar sodium fluoride. This is going to add another liter of liquid to the solution. In this second liter of liquid, we have added 0.03 molar, or 0.03 moles of every 1 liter, times the liter we added. We've added 0.03 moles of sodium fluoride. As this goes into our solution, it breaks apart to form 0.03 moles of sodium and 0.03 moles of fluoride. In our entire container now, we will have 0.03 moles of sodium ions floating around in the water, 0.03 moles of fluoride ions floating around in the water, 0.01 mole or 0.1 moles of the lead plus 2 ions in the water, and 0.2 moles of the nitrate ion in the water. In order for us to determine whether or not we're going to get a precipitate, though, I don't need to just know how many moles. I need to know what the concentration is. I need to know the moles per liter. We added 1 liter of each of the different solutions. So now we have a total of 2 liters of solution. Moles divided by total volume will give us molarity, the concentrations. So the concentration of my sodium ion will be 0.015, the fluoride ion 0.015, the lead ion 0.05, and the nitrate ion will be concentration of 0.1. Because I'm interested in the formation of lead fluoride as a possible precipitate, these are the concentrations that are relevant to what I'm trying to determine. To determine if lead fluoride will precipitate, I need to find the concentration of lead and the concentration of fluorine ion in the solution and compare it to the KSP. Remember, the KSP is an equilibrium constant. It will let us know whether or not we're at that maximum amount of lead fluoride that the water can sustain in solution form. If we have more ions than the water is capable, if the product of these numbers is bigger than the KSP, well, then we have more ions than the water can hold, and it's going to drop some. We'll get a precipitate. If the products of these numbers are less than the KSP, then water is going to be perfectly capable of sustaining them. So because we're interested in lead fluoride, I'm going to write down the equilibrium reaction for the dissolving of lead fluoride. Lead fluoride breaks down to form lead ions plus 2 and fluoride ions minus 1. Of course, since lead fluoride is potentially an equilibrium situation, we can use two-way arrows here. The KSP expression for this salt would be KSP equals lead ion times fluoride ion squared. Remember that the coefficients from the balancing become the exponents in our KSP expression. We're now going to substitute the amount of lead that we determined that we got from the lead nitrate and the amount of fluoride that we were put into the solution from the sodium fluoride into this expression to see what we get. We're going to call this a QSP. It's a solubility product quotient. The quotient is what we call an answer when we multiply things. I'm not calling it the KSP because we don't know if we're at equilibrium. So I'm just going to change it to QSP. It's kind of like a trial KSP. We're going to try the values and see what we get. We've already determined that the concentration of lead in this container is 0.05 molars. And the concentration of fluoride ion is 0.015 molar, which I have to square. Students often ask me if I have to times it by 2 because of this equation. Well, in this case, no, I don't. My fluoride did not come from lead fluoride. As you saw from the breakdown that we just went through, all of the fluoride ion came from sodium fluoride. So these numbers represent the concentration of lead and fluoride in the actual container we have. When we do the math, we come to a value of 1.2 times 10 to the negative 5. To determine whether or not we'll get a precipitate, we actually need to compare this trial number to the actual KSP for lead fluoride. Looking it up on a chart, we find that the actual KSP for lead fluoride is 3.3 times 10 to the minus 8. The number that we calculated is much larger than that. We're at the order of 10 to the minus 5. We clearly have many more ions than the water is capable of sustaining. Our QSP is much larger than the KSP, and anytime we come to a situation where QSP is greater than KSP, the precipitate will form. Now, quite often when I give you a question, I'm going to give it to you at the point of, here are the ion concentrations. I'll give you a question that's already at this point, where you know the concentration of every ion in the solution. All that previous work will have been done for you. So all you would need to do, if we were given this as a starting point, is determine which two ions are the most likely combination to form a precipitate. And you'd use your solubility rules here to pick the most insoluble candidate. And then plug those values into a KSP expression, which we're now calling QSP, and compare it to the actual KSP. If there's more than the max, we get a precipitate. If there's less, we do not. I have lots of available practice for you guys to work on for this. There's lots of questions out of our textbook in chapter 17. There are the workbook questions at the end of the workbook in the correspondence section, which are numbered pages 190 to 197. I'm going to get you to omit the questions on page 198 because they ask you to make too many assumptions and I find them confusing. So we're just going to omit those few. And then at the front of our workbook, pages 4 and 5 you've already started on when we started taking a look at solving problems and involving common ion. But there's also some more on page 5 and into page 6 involving predicting precipitates. Now there's a small section of questions there on common ion involving acids and bases. We're going to leave those alone for now. I'm going to teach you how to do those questions in our next unit on acids and bases. Sometimes I choose to teach the acids and bases unit first, at which point this is a good place for us to review. This time we did solubility first, so you can skip the questions about common ion with acids and bases. So on pages 5 and 6, I'm only worried about the precipitate formation questions.